Hello everyone, this is Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So before we begin, Simran had a few questions. Simran, you can ask them now. Simran?
Yes, ma'am. Good evening, ma'am.
Yeah.
The doubt is from previous weeks. So I just want to know how the longitudinal stability is affected by tail volume ratio.
Okay. Longitudinal stability affected by tail volume ratio. Okay. When we do the revision, I think that formula will come up. We'll discuss this then. Is that all right?
Okay, ma'am.
Okay. Any other question?
Yes, ma'am.
Yeah.
It's one of the question from 12th week.
Okay.
How the damping ratio is related with stability.
Okay. Yeah. These questions we'll discuss now. Yeah. Anything else other than these two?
And one is elevator deflection with stability, like how the elevator deflection affects the stability of aircraft.
So elevator is a control surface. None of the control surfaces affect the stability. None of the control surfaces affect the static stability. Okay.
Okay.
So you're deflecting the elevator only to control your aircraft. It does not change the stability in any way.
That means if we deflect the elevator in a positive direction or say positive alpha or negative alpha, it does not affect the static stability of aircraft.
No, it does not affect. It does not change anything because the
Oh,
slope remains same. That CM versus alpha slope remains the same.
got it.
So we'll begin. These two questions will come during the course of the contents. We'll just discuss this then. Okay.
Okay, ma'am.
So just a brief recap of dynamic stability. Till now we were discussing static stability. Dynamic stability of an aircraft, we have two new terms involved. So CL is the coefficient of lift. Until now we were discussing only CL naught and CL alpha into alpha, and the control term CL delta E into delta E. Two new terms have been introduced for dynamic stability, that is with respect to Q and alpha dot. What is dynamic stability? Dynamic stability was the tendency of an aircraft to go back, whether or not it goes back to equilibrium when subject to a disturbance, and whether or not it goes back to equilibrium over a period of time. Okay, so when the time aspect comes into play, you have two new parameters, that is pitch rate Q and alpha dot, rate of change of angle of attack. So both of these terms are over a period of time, pitch rate and rate of change of angle of attack. Okay, so these two new terms come into play in your CL, that is coefficient of lift, and CM, that is pitching moment coefficient. So these two new terms are added into your linear approximations of CM and CL. Okay, so you can see them here and here. Now this QC by 2V is just done so that you non-dimensionalize the entire equation. Every other term is non-dimensional. Alpha and delta E are in radians and they are non-dimensional quantities. Only Q and alpha dot had a per second. So it was not non-dimensional, it was radian per second. Now it's multiplied by C and divided by 2V to remove this dimensional term. So similarly, when that is done, the CMQ will also have this QC by 2V. So CMQ would be dou CM by dou QC by 2V. Okay, so that would be CMQ. Similarly, CM alpha dot would be dou CM by dou alpha dot C by 2V. Okay, similarly for CL. Now, what happens when you have a pitch rate? When you have a pitch rate, there is a change in the angle of attack at the tail, which is approximately equal to this QLT by V. LT is the moment arm, Q is the pitch rate, V is the velocity. So this change in angle of attack at the tail is approximately equal to this QLT by V. This generates a force delta L, an additional force, additional lift delta L, which produces an additional moment, this one. Okay, so it has a negative sign, you can see, because it is producing a pitch down. Okay, it's producing a nose down moment. Okay, so if you're this is your tail and is subject to a positive delta alpha, it produces a positive change in lift delta L, and it produces a pitch down moment, which is why you have a negative sign. So their non-dimensional terms also have similar signs. They're derived just according to how we had derived in the previous cases. Then we saw how it was analogous to a second order system, a typical second order system, that is the spring mass damper. This is the equation for a spring mass damper, where the stiffness coefficient is K, damping coefficient is C. The states are X and X dot. If we equate it or make it analogous to our aircraft system, the states are Q and alpha dot. Okay, so they are alpha and Q. So alpha dot. Just a minute. Just erase that. Yeah. So the states are alpha and Q, and the analogous terms to C and K. So it would be analogous term to K would be Cm alpha. Cm alpha is like the stiffness of the aircraft, how much it withstands a perturbation. And Cmq is analogous to damping. Cmq tells you whether or not it comes to equilibrium and how much time it comes to equilibrium and how it comes to equilibrium. So if this is your equilibrium line and it is subject to a perturbation, whether it comes back to equilibrium oscillating or it comes back smoothly to equilibrium or it deviates from the equilibrium is what the CMQ tells you. So the damping coefficient is analogous to damping coefficient. Okay, so Cm alpha is like the stiffness and CMQ is like the damping coefficient. Okay, now we saw the forces required for the analysis of dynamic stability. There are three types of forces: aerodynamic, gravitational, propulsive. Aerodynamic, we know, lift and drag. Gravitational is acting downwards. Propulsive is thrust. Now, when we have two equations for equations of motion to analyze the dynamic stability. There you have these two equations: force equation and moment equation. Both are written in the inertial frame, but it is convenient for us to measure several quantities in the body frame. So we have derived this relation. So we have two frames of reference for this dynamic stability analysis. They are the inertial and body frame. In our case, due to the short duration of analysis of dynamic stability, we assume the Earth fixed axis to be inertial axis. It is not actually inertial because there is angular momentum of the Earth, which we are not considering because the dynamic stability analysis is done for a short period of time. So the inertial axis that we've taken in this case is the Earth fixed axis. And the body fixed axis, you know, it's what we've been doing all along, what we've been using all along, the X, Y, and Z along the body, which is fixed and moves along with the body. So we need a relationship between the body frame and the inertial frame to represent these two equations of motion. For that, we've derived this transport theorem. Okay, so where if A is a vector that's represented in both body and inertial frame, it's the same vector. You can represent it in body and inertial frame, and doing the differential in both body and fixed inertial frame, you can see that we obtain this relation where the omega cross A term is what relates the body frame derivative to the inertial frame derivative. Now, using this relation in your equations of motion, we can come up with two equations of motion in which we can conveniently use the body frame measured quantities and equate it to the inertial frame by means of this omega cross H. I keep forgetting to remove this M. There is no M here. Okay. So dVc by dt is what was measured in the inertial frame. How do you represent it in body frame? How do you equate these two? You have this omega cross the vector term. Omega cross A is the term. A, in place of A, we use the vector Vc. Similarly, for this moment equation, the vector is H. So you have an omega cross H term. Now, after this, we saw the various vectors represented in the body frame. These are all represented in the body frame. F force, so Fx, ijk, small ijk are the unit vectors in the body frame. Vc has three components, u, v, w. Omega, the angular velocity, has p, q, r, the moment vector, and h. Okay, so these are the quantities that are represented in the body frame. What we did was we took each of these forces and we derived the equations of motion. So this is the final 6 degrees of freedom equations of motion. Okay, so the states here are u, v, w, and p, q, r. So the 6 degrees of freedom, the dynamic states are u dot, v dot, w dot, and then p dot, q dot, r dot. Okay, so these are the 6 degrees of freedom equations of motion that are used to represent the dynamics of an aircraft. So the forces that is on the right hand side, you have these forces: aerodynamic forces, propulsive forces, and gravitational forces, like we discussed previously. Propulsive forces, in this case, it's just the thrust, so it's Ft. Aerodynamic forces are lift and drag. Now, how do we represent the orientation of the aircraft? So one of the ways in which we represent that we discussed previously was the Euler angle representation, where we had seen that the psi and theta are not yaw and pitch. Okay, so psi is rotation about the earth fixed, that is the inertial z-axis. Now, first we initially rotate about the z-axis, and then we rotate about the new axis, the new y, x1, y1, z1. Then we rotate about the new y1 axis to get theta. So these two angles are not to be confused with yaw and pitch, which are measured in the body fixed axis. Okay, so they are not the same thing. Now, where do these angles come into play? It comes into play in this gravitational force. It does not come into play in the aerodynamic or the propulsive forces because both of them are measured in the body axis. The Euler angles only come into the equations of force due to gravity because these are measured in the inertial axis. Okay, so which is why you see them here, and they also come in the PQR terms. Okay, we discussed previously why psi does not appear in this gravitational axis because psi is the rotation about the final z axis. Okay, the final z axis is coincident with the gravity. So there will not be any psi term in these set of equations. I explained this in the previous week. Okay. Next, we considered only the longitudinal dynamic stability. Longitudinal dynamic stability is the motion in the x-axis, xy plane basically. So x-axis, xz plane, I'm sorry, x-axis, z-axis, and the rotation, that is pitching moment in the y-axis, pitching moment about y-axis. Okay, so you have three terms out of the 6 degree of freedom equations. We take three of them. Three are the motions in the longitudinal plane. So you have u dot, v dot, and q dot. These are the three quantities that we will be analyzing. Now, to see how it behaves when subject to a perturbation, we take the aircraft initially at steady state. What is steady state? It's the equilibrium condition in our case. And we subject it to small perturbation. So we take these quantities where the subscript 1 denotes the values at steady state. So you have u1, v1, w1, all these values measured at steady state. So it's the velocity at steady state. This is the angular velocity at steady state. These are the Euler angles at steady state. These are the forces at steady state. Now they're all subject to a small perturbation. The small quantities, small u, small v, small w, they are all the perturbed quantities. Okay, so they are the small perturbations that we've introduced to the aircraft at equilibrium, at steady state. Now, when we derive the equations of motion, we see that it is convenient for us to choose a stability axis that is along the final velocity direction. Why? It simplifies the equation greatly. The final velocity direction, if you align your axis in the final velocity direction, the x-axis of the stability axis is coincident with the velocity. So the velocity will not have components in the y and z axis, and the final equations become extremely simplified. So these are the final 3 degree of freedom equations. 3 degree of freedom, that is for longitudinal stability. So you have small u dot, small w dot, and small q dot. Okay. So these are the equations of motion that are used for, this is I, y, y, okay. That are used for longitudinal stability analysis, longitudinal dynamic stability analysis. Now we take each of those terms, each of these fx, fz, and m, these terms to analyze them separately. We write down their linear approximations that are varying with u, delta e. They also vary with axis, varies very negligibly with the pitch rate or the rate of change of angle of attack. So we can ignore these two quantities in the first equation, but they are very prevalent in the second two equations. So these two terms cannot be ignored in the z direction motion or the pitching moment motion equation. Okay, so now we've written down these three approximations, linear approximations, and this u by u1 is done again to non-dimensionalize the equation. Okay, now we take each of these equations and analyze them separately, find out each of those derivatives. So the first derivative in the first equation is dou fxa by dou u by dou 1. Okay, similarly, the other three derivatives we have derived. Substitution of these three derivatives in the first equation gives you this. Okay, that gives you this equation. Now that equation is represented, it's simplified in this way, where xu is nothing but this term, x alpha is nothing but this term, and x delta e is nothing but this term. Okay, this comes from the main equation of motion. You can see in the previous case, So it's this, right? So that comes from there. So you got your first equation, that is u dot equation. This is written to finally simplify the equation in terms of a matrix. Similarly, you perform the same analysis for fx, fz in the z direction, motion in the z direction. You can see that two new terms have come here. That is dou fz a by dou q c by 2v. V in this case is u1. Similarly, the alpha dot, the term that varies with alpha dot. Both of these terms have a negative sign. Why? Because your lift is produced upward, but your z-axis positive is downward. So there is a negative quantity written here, negative sign introduced in these two terms. Now CLQ and CL alpha dot are given as per these two equations. Okay, so CLQ is, I think this is asked in one of your questions, so this would be CLQ. I think they've asked CMQ, but you get the hang of it. Now, if you substitute these derivatives back into the main equation, like in the previous case, you get your W dot equation. This also you can represent using, instead of XU, you will have ZU. So this term would be ZU. This just like the previous case. I have not written that here, but you can use that. Have those two terms that are associated with Q and alpha dot. And in those two terms, you have CM, QM, C and alpha dot, which are represented here. This, I think, is what is asked in your assignment. And CM alpha dot. CM delta E, we have been studying from before. So control surface delta E, how much deflection of your control surface, how it affects the CM. All of this, you get this equation. Similar to the previous case, you had XU, ZU, you have MU, M alpha dot, MQ, and M delta E here. Now, so these are the three equations that we've got. I've just written them together. When you write them in a matrix form and apply the Laplace transform, you get a neat little matrix here in the term of AX equal to B, okay? Where X is your state vector here, okay? So you get a neat equation. Now, when you solve this equation, when you take the determinant of the matrix A, should have been a different A here, just imagine that to be A prime, okay? So when you take the determinant of that A matrix and equate it to 0, you take determinant of A equal to 0 gives you the characteristic equation. So this is a fourth order characteristic equation in S, which can be decomposed into two second order systems. Okay, this is to be solved numerically, and we can see that they can be decomposed into two second order equations. When we analyze these equations, we can see that these roots are always a pair of complex conjugates. What does complex conjugate indicate here? Complex conjugate roots A plus IB, A plus or minus IB, C plus or minus ID. What do they indicate here? The complex conjugate means that the motion would be oscillatory. Okay, whether it goes to equilibrium or deviates from equilibrium, it would be oscillatory. What tells you whether it goes to equilibrium or not? So you have two roots, two pairs of roots. You have A plus or minus IB and C plus or minus ID. So what term in these two roots tell you whether it goes to equilibrium or not? Can someone tell me? So because we have this complex conjugate, we know that it is oscillatory in nature. But how do we know if it goes to equilibrium or deviates from equilibrium? Can someone tell me? Which of these terms, which of these quantities, A, B, C, D, which of them indicate whether it goes to equilibrium, that is, if it's stable or not? It's a sign of any of these parameters. Which one? Okay, let me just help you with that. So if these real parts of these roots, that is A and C, if they are negative, then only it will go to equilibrium. If they are positive, it will go away from equilibrium. So for it to be stable, it should be less than 0. Okay, if it's equal to 0, it will be neutrally stable. it will keep oscillating about with the same magnitude. But if it's less than 0, it will oscillate back to the equilibrium. So it will be like this. So decaying amplitude, and it will go in eventually to equilibrium. If it were positive, if A and C were greater than 0, it would oscillate and go away from the equilibrium. It will not come back to equilibrium. It is not stable. Okay. So the negative, the real part of the root should be negative. A negative real part indicates stability. Okay. Two pairs of complex conjugate I had mentioned, A plus IB, C plus ID. Now, whichever has a higher, so if A, magnitude of A is greater than magnitude of C, then that is the short period mode. So it goes fast to your equilibrium. So it will oscillate fast and come to equilibrium. If the long period mode takes a longer time to come back to equilibrium. It will come to equilibrium, but it takes a longer time. So that's the difference between the two cases. Okay. So what was the Routh criteria in this case is all of these quantities should be greater than 0. That is first condition. Then for a fourth order equation, this is another condition. Okay. Then sir had taken one of these conditions out of these A, B, C, D, E greater than 0. We had analyzed E greater than 0 to get this condition necessary for stability. Okay. Now this was just a brief recap of second order system. Again, I had taken the typical spring mass damper system, derived its characteristic equation. How? Taking x equal to e raised to lambda t. And if you take the second derivative, first derivative, you get its characteristic equation like this. If you solve it, you get two roots like this. This is just to tell you how we came to this A plus IB, C plus ID. Okay. Now, when you analyze this equation and compare it to a typical second order equation, you get the damping ratio eta and natural damping frequency omega n. Okay. This is just a recap of a spring mass damper second order system. Okay. Then we had seen three approximations. That was short period mode approximation, a phugoid or long period mode approximation, and pure pitching motion. For this approximation, we assume that u remains constant. So it will oscillate quickly and come to equilibrium. We assume that the velocity doesn't change much. Then you get a 2 cross 2 matrix when we neglect u. Okay. Now solving that, you get this as the characteristic equation, and you get a natural frequency and damping ratio as such. Okay. Similarly, we perform the analysis of phugoid mode. In this case, we assume that the alpha doesn't change. This is not a very great approximation, but we can still work with it. We assume that the alpha does not change. So if it's the phugoid mode, takes a long time, oscillates about a long, we assume that the alpha doesn't change. Okay, so it remains with the same angle of attack over the entire oscillation, which is not true, but it's an approximation. This leads us to this equation of motion and the two quantities, natural frequency and damping ratio. Okay. Next was a pure pitching motion. Here, okay, this is not there. Pure pitching motion. So in this case, we have this characteristic equation, and these are the two quantities. Now the next slide shows you a comparison of all of those quantities. We can see that the pure pitching motion and short period mode there is one term here. That is the only change. That is due to the plunging motion. In the pure pitching motion, you have only this rotation. There is no motion in the X or Z direction. But in the short period mode, there is an oscillation. It oscillates fast to the equilibrium, but there is an oscillation. That means there is a translational motion. So this plunging motion is what contributes to this additional term. Due to the absence of this plunging motion or translational motion, that term is absent in this pure pitching case. Okay. Similarly, for the damping ratio, there is that term, this additional term that comes in the short period due to the plunging motion, which is absent in pure pitching. Now, these were the questions of week 11. So they had given the 4 roots of the characteristic equation. And the first question was the roots for short period mode. Short period mode has a larger negative, larger real part. So the two sets of roots here are, one is -4 plus or minus 2i or 2j. The other one is minus 0.002 plus or minus 0.1 j. So in this case, which would be the short period mode? Which would be the long period mode? Which roots would indicate short period? Which roots would indicate long period? Can someone tell me? I just told you the larger magnitude would be larger magnitude would be. So which one is the short period mode? Am I audible?
Yes, ma'am. It's -4 plus -2j. It's short period.
Correct. So it's -4 plus or minus 2, plus or minus 2j. That's the correct one. And the long period is the other one, minus 0.002 plus or minus 0.1j. So the next question was find the natural frequency and damping ratio for the Fugard mode, Fugard or long period mode. So you take the second root, that is minus 0.002 plus or minus 0.1j. Now, how do you find the characteristic equation? It was s square minus sum of roots s plus product of roots equal to 0. Okay, so if you do this, you get s square minus sum of roots is minus 0.004 s plus product of roots is, someone just tell me this, what is the product of roots? What are the products? Just calculate this quickly. You solved this assignment, right? So can you just calculate it? Okay, calculate it, and then you equate it to your typical second order equation. You get s plus omega n square equal to 0. You can calculate omega n from here, and then you can calculate eta from here. So what is this product of roots term?
It's 0.01 000 and then 4.
Okay. Are you sure? Okay. So when you take the square root of that value, you get the natural frequency to be, you get it around 0.1. Okay. And then you do 2 eta omega n equal to 0.004. And then you get eta to be 0.004 by 2 into 0.1. And you get 0.004. Right? That is the answer. 0.02, sorry. So this is the answer. So this is how you calculate the natural frequency and damping ratio. Next question was to find the range of k for which this equation would be stable. Now this is the third order equation, so you can use the Routh criteria. So one condition is, so let's just take this, s cube plus 3s square plus 3s plus 1 plus k equal to 0. Now the coefficient of s, let's take it to be a is 1, coefficient of s cube, coefficient of s square, b is 3, coefficient of s, c is 3, and the constant is b, which is 1 plus k. Now all of these coefficients must be greater than 0 is the Routh criteria. A, B, C are greater than 0. D has to be greater than 0. That is, D should be greater than 0. That means 1 plus k should be greater than 0. Or k should be greater than -1. That is one condition. Next condition is from the Routh criteria or the Routh table. So you make the Routh table. How do you make the Routh table? You write A, B, C, D. So what are the quantities? And then you have, let's say, A1, B1, and so on and so forth. Okay. So this is for a third order equation. So what is A1? Let's just make this table with the actual values. It is 1, 3, 3, and 1 plus k. Here you have A1 and B1. What is A1? A1 is minus 1 by B into determinant of A, C, B, D. That is minus 1 by B was 3, determinant A was 1, 3, 3, 1 plus K. So you have, what do you get finally? You get K minus 9 by minus 3. Okay, so the first column of the root table must be greater than 0. A and B greater than 0, we've already checked. So A1 has to be greater than 0. That is our condition. So A1 was what? 1 plus K minus 9 should, okay, there is also a negative sign here. Minus plus should be greater than 0. Okay, so K should be less than 8. This is your second condition. K should be greater than minus 1 and K should be less than 8, which is this one. So this is how you make the root table, and the criteria is that the first column of the root table must be positive. For a third order equation, you get only 3 rows, but for when it increases order, you get more rows, and all quantities in the first column must be greater than 0. That is the condition for dynamic stability, for stability. Next question, there are a couple of questions which were similar. For an aircraft, in first flight, it was flown from north to south, and in second flight, it was flown from south to north. For both the flights, the indicated airspeed and altitude are same. A steady wind was known to be blowing from north to south. The damping ratio of the first and second flights are eta1 and eta2 respectively. Which of the following options is correct? We know that this damping ratio is not affected. You can see the 3 modes we can see. So none of these terms have any direction of flight or the oncoming velocity, oncoming wind. There is no, what was the question? It said steady wind was known to be blowing from north to south. Okay, so none of those terms affect these damping ratio or natural frequency. The terms that affect these are mentioned here. Okay, the oncoming velocity has no effect, or the direction of flight has no effect. So both natural frequency and damping ratios will remain same for both the flights. Okay, since no other parameters are changing. Now these are the questions of week 12. So what was the question, Simran, you had asked? Was it this one? Something from week 12 you had asked, Simran? Okay, anyway, we'll move ahead with these questions. Now, canard, what's a canard? We had discussed this during static stability. So if this is your aircraft, okay, you have a wing here and you have, okay, I'll just draw on a line. So you have a wing here and you have a tail, okay? A similar surface attached ahead of the wing, similar symmetrical or any airfoil cross section attached ahead of the wing is called a canard. This is a canard, this is the wing, and this is the tail. Okay, so how does the canard affect stability? Okay, so now let's see. If this is the CG of the aircraft, we'll see the contribution of each of these parameters. Okay, so now the wing. So when it's subject to a positive angle of attack, let's say a lift is produced here. Assuming it's a symmetrical airfoil and it's subject to a positive angle of attack, you have a lift produced here. Now this lift, what is the moment about CG? It is pitch up. Okay, it pitches up. Now, and there is no restoring moment. Okay, so you understand it doesn't contribute towards stability. So if your aircraft has a positive angle of attack, it has moved up, it is nose up, there is a positive lift produced at the wing, and it contributes to again pitch up. Okay, it's not a restoring moment. What about at the tail? So at the tail, again, you have a positive lift produced here, but here it contributes to a restoring moment about CG. So wing is stabilizing. Okay, it's not stabilizing. Tail is stabilizing. What about canard? We had discussed this during static stability. Again, it is subject to a positive angle of attack. So there is a positive lift. So this again produces a pitch up motion. There is no restoring moment. So your canard is also destabilizing. It's not stabilizing. What does it mean? For stability, for static longitudinal stability, what did we need? If CM, this is CM versus alpha, you needed a negative slope. Negative slope meant stabilizing. So the wing contributed towards, so when you had a positive alpha deflection, it gave you a positive CM. It did not have a negative slope. But tail, for a positive alpha, you had a negative CM. So tail contributes towards a negative slope. So you have negative CM alpha. This has positive CM alpha. And this also has a not restoring component, non-restoring component, further destabilizing component. So you have a positive CM alpha. Okay. So canard contributes towards a destabilizing. It's a destabilizing in nature, contributes towards positive CM alpha. Okay. So now we know that static stability will, what will be the answer? Static stability will
Decrease.
decrease, correct. Now for short period damping, now let's go back to the short period damping equation. Okay. Short period damping is this. Now here, none of these quantities change when canard is introduced, except which quantity? This M alpha. M alpha is proportional to CM alpha. Okay, so this changes. CM alpha is positive. The contribution of canard is positive. So the originally, suppose if CM alpha originally was -10, when you introduce the canard, it becomes less negative. So it becomes maybe -5. These are just random values. I'm just telling you. So this M alpha will change. This omega n, that is the natural frequency of short period mode, comes into play even in the damping ratio. So you can find out how it affects the damping ratio of short period mode, how the canard will affect damping ratio of short period mode. Okay, there. Which of the following is responsible for pitch damping and yaw damping? Pitch damping, we had seen, what was the term? CMQ, right? This was the pitch damping. Similarly, for yaw damping, when sir had taught us the lateral and directional dynamic stability, for yaw motion is Cn and the derivative is Cnr. Okay, so this is the right answer in this case. Now, pitching moment coefficient due to lag in the downwash field can be given as, this is a direct formula which is given in the previous slides. It's given in sir's lectures also. I will not be discussing this. Then, an airplane has the longitudinal routes as given in the figure below. Assume that 2 degree of freedom approximation for longitudinal dynamic modes is valid. What does that mean? That you can decompose this fourth order system into 2 second order systems. Here the 2 routes are -5 plus or minus 6i, and the other one you have repeated routes at the origin. Can you please repeat second question? Second question, which is responsible for pitch damping and yaw damping, these are given directly in the derivations when dynamic stability was discussed. Okay, so CMQ is the term that is damping, that represents the damping of the second order system in longitudinal case. I had told you this, we had seen when you equate it to mx double dot plus cx dot plus kx equal to 0. I told you that K is analogous to CM alpha and damping is analogous to CMQ. Similarly, when you do it for the yaw case, it would be CNR, which is, I think, given in week 11, the penultimate or the last lecture it's given. It's directly given, it's a direct question. Yeah, so here you have these 4 routes, that is -5 plus or minus 6i and 2 repeated routes at the origin, 0. The question here is, what is the value of short period damping ratio? Short period is the one with a larger magnitude, larger real magnitude. So this has a larger real magnitude. How do you find the damping ratio? You write your second order equation. Take this root. These are the roots for short period because it has a larger real part. Magnitude of real part is larger. The magnitude, not the sign. When you take sum of roots plus product of roots equal to 0. Okay, the roots in this case are these 2. So when you solve it, you equate it to, just now we have done this question, equate it to 2 eta omega n s plus omega n square equal to 0. You can find out the damping ratio eta from this equation when you equate these two equations. Next, they've asked you what is the value of undamped natural frequency. I think it should be underdamped. It should be underdamped. So now you found out the damping ratio. You can find out the damping frequency in the similar manner. Okay. Okay. So now we'll go over. We'll just brush over the concepts of the previous weeks. That is the static stability part. We'll just go over it. So we initially began this course with what is static stability. Static stability was the initial tendency of any system to go back to its equilibrium when it is subject to some disturbance. It was just the initial tendency. The time aspect was not given in picture. That is how it varies from dynamic stability. An aircraft, it was if it was flying at equilibrium, at steady state, when it is subject to some positive angle of attack deviation, its initial tendency, that is, if it has a restoring component, restoring moment to come back to the equilibrium, then it is considered longitudinally statically stable. Okay. Then we discussed aerodynamic center. Aerodynamic center is the point about which this pitching moment is independent of angle of attack. Okay. Pitching moment is independent of angle of attack. Now, why we chose this point? Because all of the forces act about a point of pressure, Cp. But this point keeps changing with angle of attack. So throughout the flight, this point would keep varying. It would become highly inconvenient for us to write the equations. So we picked a point which is independent of the angle of attack. So we represented all of the forces. So if this was your center of pressure, Cp, and this is AC, we represented, we translated, we moved all of the forces and moments to the aerodynamic center. So when you move the forces, lift and drag, it also comes with a moment. Okay, so there's also a CMAC. Okay, when you transfer forces from one point to another, it comes with a moment. Okay, then we discussed what is trim. Trim is where net forces and moments are zero. So if we take Cm versus alpha, this point would be trim. Okay, then we represented, okay, if we saw the convention for pitching moment, we know pitch up, that is nose up is positive, nose down is negative. Then we saw the equation for the pitching moment. So you have, this is Cm versus alpha. We know that the condition for static stability, Cm alpha should be less than 0. We just discussed this in the previous question. And we need Cm naught to be positive. Why? So that we can trim the aircraft at a positive angle of attack, which is necessary, which is preferred. Okay, Cm not positive is not affecting the stability in any way. It is just so that you can trim the aircraft at a positive angle of attack. How do we ensure Cm not to be positive? There are several ways. One, if we do not consider tail, how do you ensure? You ensure that your CMAC is positive, greater than 0. Now, CMAC for a cambered airfoil is less than 0. For a negatively cambered or reflex airfoil, you will have CMAC greater than 0. Okay, so for cambered, you have less than 0. So for reflex, you have greater than 0. Okay, so that is one way to ensure Cm naught greater than 0. Another way is you introduce a tail. Now we see the wing contribution and the tail contribution. So the wing contribution has the CMAC wing and the CL naught. This entire thing is Cm naught of wing, and this entire thing is Cm naught of tail. So Cm naught is equal to Cm naught of wing plus Cm naught of tail, and this entire thing should be greater than 0. So one way is CMAC wing should be greater than 0. That is use a reflex airfoil. The other way is this quantity should be greater than 0. That is AC should be behind CG. Yeah. So this quantity should be positive. Okay. That is one way. The other way is to ensure that this quantity is positive. How do you ensure that? This tail setting angle, make it negative. So you set your tail at a negative angle of attack, and this wing angle, this is one way. The other way is to ensure that your wing setting angle is greater than your tail setting angle. Okay, these are the ways to ensure that Cm naught is positive. Why do we need Cm naught positive? to trim the aircraft at positive angle of attack. Okay. Now, yeah. So if this quantity has to be positive, you need to have the aircraft ahead of CG, but then it doesn't contribute towards static stability, which is why we introduced tail. Okay. Then we discussed neutral point. Neutral point is analogous to neutral point of an aircraft is analogous to aerodynamic center of a wing. So it is the point about which Cm alpha is 0. Cm doesn't vary with alpha, just like the aerodynamic center for a wing. Then we derive the equation for this neutral point in terms of wing. This is the equation for the neutral point. Then we saw what is static margin. Static margin is a quantity, is a measure of the stability of an aircraft. Okay, it is related to the neutral point like this. It is the negative of the slope of dCm upon dCl. So dCm upon dCl has a negative slope. So this term would be positive. For a statically stable aircraft, this term would be positive because your dCm upon dCl is negative. Just write this. This is Cm, Cl. Okay. So these are just some terms. This is downwash angle and the rate of change of downwash angle with alpha. These approximations we have studied, and these will be used here and here. So I've just written the formulae. VHS tail volume ratio, and this is very important. This relation between 2D airfoil and 3D wing, how they affect. So for a 2D airfoil, we don't consider the wingtip vortices. So there is that contribution is accounted for in this relation. Okay. Then we saw controls. What does control do? Control surface in the longitudinal case is the elevator. What does it do? So you have your Cm versus Cl. This is Cm versus Cl. Now at trim, this is your Cl trim, right? So if you want to fly your aircraft at a different Cl trim, so if you want to fly it at a different velocity and still have trim conditions, you need to change your Cl trim. How do you change your Cl trim? You translate this graph. So this is your new Cl trim. So what does the elevator do? It effectively translates your Cm versus Cl graph. It does not change the slope. This was one question that was asked. It does not change the slope. That means it does not affect the static stability of the system. Okay. It only translates. It does not change the slope. So control surfaces have no effect on static stability of the system. Okay. How does it do this? So you have, this is your tail, and it has a control surface elevator. So the tail was initially symmetrical airfoil. It had 0 camber. So when you deflect your elevator, it has a camber. What is the property of a cambered airfoil? It generates lift even at 0 angle of attack. So this is how this changes your Cm versus Cl graph. Okay. Changes as in it does not change the stability, it just translates the graph. Then we saw the two parameters Cl delta E and Cm delta E. We saw their signs. Cm delta E is negative. Then we saw the control surface effectiveness parameter tau, dou alpha T by dou delta E. This also comes into play. A similar term comes for the other control surfaces. Then we saw the delta E trim, delta E required to trim the aircraft at the new Cl trim. This again, you will have this kind of a graph. So delta E and this is Cl trim. So you have, this is delta E naught plus dou delta E on dou Cl trim into Cl trim. So this is the delta E required to trim the aircraft at given Cl trim. Okay. And then we saw the sign conventions. We saw Cm naught is positive, Cm delta E is negative, and there's a negative sign. So delta E naught is positive. Delta E naught is positive. Now this term is positive for a stable aircraft. This term is negative. So this entire thing would be negative and you have a negative slope. Okay. Then we moved on to directional stability. We saw the conventions. Conventions for directional stability is right wing back. So that is positive yawing moment. So turning your right wing back, left wing forward is considered positive yawing moment. Okay. Then the other convention was positive side slip angle. So if this is your fuselage reference line. If your oncoming velocity is towards the right, then it is considered positive beta. This is your fuselage reference line. This is oncoming velocity. Positive beta. Okay. Then control surface convention. If you deflect your rudder towards the right, okay, if you deflect the rudder towards the right, towards the left, it is considered positive delta R. So when you deflect your rudder towards the left, it produces a lift in this direction and it yaws the aircraft to the left. Okay. So that is considered positive delta R. Now, we saw that due to this induced beta, so if it's subject to a positive beta, the restoring moment should be what? You should turn your aircraft, you should yaw your aircraft in this way to negate this induced beta. Okay. So your Cn beta should be positive. For induced positive beta, for positive induced beta, you need to have positive Cn. So your Cn beta should be positive, greater than 0. Now we see that due to an induced beta, the force that is generated, so due to positive beta, force produced on the tail. So this is the tail. There is an induced beta here. The force is produced here, Fy, but your y direction positive is here. This is your positive y-axis. So your Fy is negative. That is, the Cy beta is negative. So to ensure that Cn beta remains positive, you're introducing a negative sign here because your Cy beta is negative. So introducing a minus sign here to ensure Cn beta remains positive. Now what contributes towards positive Cn beta? Vertical tail, swept wing. How does vertical tail, we know how it contributes towards positive Cn beta. We saw that with an induced positive beta, it produces a restoring moment, Cn, restoring Cn moment. What about swept wing? Swept wing is this case. So when it is subject to a positive beta, the drag on this right wing increases. Okay. So there is more force here, more drag in this direction than on this wing. And this again produces a restoring moment. Your aircraft yaws towards the disturbance. So it negates the positive beta. So these two terms contribute towards positive Cn beta, contributes towards directional static stability. Okay. So this is just a summary. It's a comparison between the longitudinal and directional cases. This convention we had studied initially. This tau is similar to the case for elevator. Okay. So now your Cn delta R. So these are the three terms: Cm alpha, Cm naught, Cm delta E. Analogous to these are Cn beta, Cn naught, Cn delta R. So this is just a summary of all the conditions required for stability, for static stability. Okay. Here Cm naught is positive because we need to trim the aircraft at a positive angle of attack. In the directional case, this is Cn naught is 0 because our trim condition usually occurs at 0 beta. Okay, so your Cn naught is 0. Okay. Then we moved on to lateral static stability, and we again went on to conventions where right wing down is considered positive. We achieve right wing down, we deflect the right aileron up, so it reduces the lift on the right wing. And then we deflect the left aileron down, which increases the lift on the left wing. So overall, the aircraft rolls towards the right. So that is positive rolling moment. Now for static lateral stability, we require a restoring moment. So if it rolls, if it is subject to a positive roll, if it's subject to a positive roll disturbance, you need it to have a negative. You need it to rotate back. The restoring moment should be less, should be negative. So the CL is less than 0. Okay. So yeah, so we saw that a positive beta introduces a negative Fy, and since the vertical tail is above the fuselage, this contributes towards a negative rolling moment. So that is one of the reasons why this vertical tail is placed above. If it's below, it would contribute towards a positive rolling moment and there would be no restoring component. Okay. Okay. So this is the equation for CL beta, and we know that it should be less than 0 for stability. What are the factors that contribute towards stability? Vertical tail, high wing. And if it's a low wing, if you have a dihedral angle, it contributes towards lateral static stability. Okay. Okay. Now we moved on to stick fixed and stick free cases. So if you allow your elevator to float, so if you have this is your tail, and this is your elevator. So the lift produced elevator produces a moment about this hinge, okay, about this hinge. That is this hinge moment. CE is the chord length from the hinge point to the tail. This is CE. Now, similar to the CM and CL, we wrote down a linear approximation for the hinge moment coefficient in terms of angle of attack at the tail, delta E, that is elevator deflection, and delta T, which is trim tab. Next, we saw what is the angle at which the elevator will float if you leave the stick. Okay, so if it's not held at that point, if you leave it, if it's free, what would be the elevator angle? Assuming there is no trim tab in this case and CH naught is 0. Okay, so this would be that value. If you take, how did we do this? We equated this to 0 and found out this delta E float. Now, if you want your delta E float to be 0, if you leave the stick and you don't want your elevator to float, you need your CH alpha T to be 0. How do you get CH alpha T to be 0? One way is to have your center of inertia of the elevator located at the hinge. So then there will be, this moment will not be there because this lift will be acting at the hinge. That is one way. The other way is to have horn balance. What was horn balance? So if this is your vertical tail, right? This entire thing is your elevator. So when you deflect it down, when you deflect the elevator down, sorry about that. I'll just draw it again. So when you, this is your vertical tail and this is your elevator. When you deflect it down, this entire thing deflects. But this portion, right? This portion contributes towards negative CH alpha T. And this portion contributes towards positive. So it produces a positive moment. So it cancels out and you have CH alpha T 0. So these are the two ways to get delta E float to be 0. And what we see here is CH alpha T, CH delta E, CH delta T, all these three quantities are less than 0. Okay, if the hinge is above center of pressure, which is usually the case. Okay, then we saw the stick conventions. Pushing the stick forward, you get more velocity. How do you achieve more velocity? You reduce the CL. How do you reduce CL? You reduce the angle of attack. How do you achieve reduction in angle of attack? You deflect your elevator down. What happens when you deflect your elevator down? You deflect it down, you have a lift here, and it produces a pitch down moment, nose down moment, which reduces your angle of attack. We must remember here, this is the point that Sir has emphasized throughout the series, that delta E required is governed by the stick fixed static margin, not the stick free static margin. Delta E required equation that we had calculated, where was it? Yeah, so delta E trim, this one is governed by the fixed static margin. Okay. Okay. Then we saw the three cases where delta E float is equal to delta E required, delta E float is less than delta E required, and delta E float is greater than delta E required. And we saw what were the control force of stick forces required in these three cases. Stick force is given to us by this equation where HM is hinge moment, delta E is elevator deflection, LS is the length of the stick, and this is the distance that the stick travels. Okay, when you push it forward or backward. So when you push the stick forward, this would be delta S. Then we saw what changes when the stick is left free. Okay, the only difference would be in CLT. Okay, that is the coefficient of lift at tail. That is the only difference between the stick fixed and stick free case. So your CL alpha tail prime is for stick free case. Okay, so X bar NP prime is for stick free case. Now the next slide will show you a summary of these two cases. Now this equation relates the static margin or relates a static margin of stick free case and stick fixed case. We know for statically stable case, we require it to be negative. So stick fixed case, we know this was less than 0. Now let's analyze this term. Now CH alpha T is negative, CH delta E is negative. So this entire thing is positive. Tau is positive. This is a term that is less than 1 but greater than 0. It's a small positive quantity. These two terms are greater than 0. This is greater than 0. This is greater than 0. So this entire thing is greater than 0. So what it does is it contributes, it has a destabilizing contribution towards your static margin. Okay. So this entire thing was negative, and this has a slightly positive contribution. So your stick fixed static margin is greater than your stick free static margin. Greater as in it's more stable. Stick fixed is more stable. Okay. So this is a summary of the stick fixed and stick free case. As you can see, the only difference comes into play where Cl alpha tail, the Cl alpha tail, that is the only difference in all the cases. Okay, that is what changes the parameters. That is static margin, X bar AC, everything. Okay. So with this, we come to an end. This is our last session. So does anybody have any questions from any of these lectures? Any questions? The second half was the revision of the static stability. In the first half, we just went over week 11 and week 12. This would be our last session. So if you have any questions. Does anybody have any questions? Okay, you can go over these weekly meeting links. I'll put them up. I'll stop the sharing and I'll put up the link of the YouTube channel. So you can go over those and study them. If you have any questions, you can ask me now. If not, we can end this. Okay, if you have no questions, then I think we'll end it here. All the very best for your assignment and your exam. I hope you had a great time learning this. So with this, I think we'll conclude. Thank you. Thank you.